Okay, welcome to CHE 120. The first part of this class goes into the structure of atoms and uses that to build up an understanding of the properties of atoms, and from there to the properties of compounds and molecules. So to take a nice example, carbon can be arranged into graphite here, as shown in the pencil, or also into diamond. The same atoms, but depending on how they're arranged, we get very, very different properties. This first set of slides is maybe more review. You can certainly skip right ahead to the problems in this section, but this will provide just a little bit of background on the periodic table and atomic structure to get ready for some of the new material coming up. First, the periodic table. One very early periodic table by Mendeley in the mid-1800s. We can see he's arranged things in terms of sort of chemical reactivity and the mass of each type of atom. An important prediction here is shown in this group underneath aluminum. Mendeley predicted this Eka aluminum, basically a new element similar to aluminum in the table with these properties, and just a few years later the metal gallium was discovered, which had these properties matching his prediction, so nice evidence for the periodic table. The modern periodic table still works in the same sort of fashion, where each column is called a group. That's where we organize elements with similar properties. The rows of the periodic table are called periods, so the first period, second period, third period, and so forth. Again, the similar reactivity in each column is really, really important. So group 1 here are the alkali metals. Those are incredibly reactive. In particular, they react strongly with water. So sodium here, if you drop it into water, you can see it reacting with the water. And starting just a little bit here, starting to burn, especially as it's ignited. A sodium fire, since water is part of the reaction, you can't use water to put that out. Need different types of fire extinguishers to take that one out. And then if we go to the next element here, look at that thing blow up. The next element here, potassium, in that same group, so we expect similar properties, and in fact, potassium, we don't even need the lighter. It's reacting explosively with water right from the get-go. That same trend applies all across the periodic table. Halogens have similar properties. The noble gases are all alike. Very important theme of chemistry that we'll sort of try to explain more throughout this first part of the class. Next, let's dive into the structure of the individual atoms. So these experiments came a little bit later after the periodic table. First, this cathode ray type experiment. You put different metals in here, and people are able to realize that the particles ejected from the metals were the same no matter what type of metal was put in there. That particle was the electron. That was the first subatomic particle discovered. Then Rutherford did this gold foil experiment that showed that when he put these positively charged particles and shone them at a thin film of gold, occasionally there would be a alpha particle that bounced off of what we learned was the nucleus of the atom. Rutherford famously described this experiment as like shooting a cannonball at a sheet of paper and having it bounce back at him, because it was so surprising that the alpha particles would bounce so dramatically off of the nucleus. From that, we now have this idea that the atom consists of a nucleus containing protons and neutrons, so a positively charged nucleus, and then around it is a broad, smeared out cloud of electrons orbiting around it. We can see the charge and the mass of each particle down here, so protons are positive, electrons are negative, neutrons have no charge. The actual relative charges are really all that matters, protons positive, electrons -1. And then mass, it's important that the electrons, though they do have mass, are incredibly light. So it takes 1,800 electrons to have the same weight as one proton. So for all intents and purposes, all of the mass of the atom is in the nucleus. And the proton and neutron have each about the exact same mass. So that is where the mass of the atom is located. And we can count each of them, proton and neutron, as weighing basically one atomic mass unit. Now, again, a picture of the atom, it's almost incomprehensible how vast the atom is and how empty it is. So if you think about Mount Union's football stadium and put a small golf ball at the center, that golf ball could represent the nucleus. Then, the sort of surrounding air in the entire stadium is the sort of area which the electron is smeared out over. So you have this very, very tiny, very, very heavy nucleus in the center, huge amounts of empty space that are where the electron cloud is located. And again, that nucleus is incredibly dense. If the air were the weight of the electron, that little golf ball at the center would actually weigh as much as a few different airplanes. It's incredibly, incredibly heavy at the center there. Okay, so that picture in mind, again, we have this positive nucleus and a cloud of electrons around it. What really matters are the relative charges, +1 for protons, -1 for electrons, and the relative masses, 1 for each proton and 1 for each neutron. Then some terminology that is important in this part of the class is, in this notation, we represent a particular type of atom or isotope with the chemical symbol here. And then as a superscript to the left, we put the mass number, that's the protons plus neutrons, that's the weight. And then as a subscript to the left, we can put Z, which is the atomic number, which is the number of protons. So that's an important fact from the chemical periodic table, is that determines your chemical identity. We don't have to show that because you can determine the atomic number from just knowing the symbol as well. If the atom had a charge, that would be a superscript to the right over here, +1, -1. If we don't have anything there, then it's just a neutral atom. So again, the key fact is shown here. Some terminology, two atoms with the same protons but different neutrons are called isotopes. And again, because of the charges of each, an atom would have an equal number of protons and electrons. So with that out of the way, we can do our first example. Here's 56 iron. How many protons, neutrons, and electrons are in that isotope? Okay, so if we look at our periodic table, we can identify iron there, shown here. This is sort of the key facts about it. So up top is the atomic number. We can see atomic number is the number of protons, so that's just 26 off the periodic table. How many neutrons? Well, the mass number is protons plus neutrons, so the mass number is this number up here. 56 is equal to protons, 26 plus neutrons, which I'll represent as N. So to make that equation work, we get subtract 26 from both sides and get 30 neutrons. 56 minus 26 is equal to N. And then how many electrons? Well, we see there's no charge here. So in this case, it's a neutral atom, and protons and electrons are equal, just 26. Okay, next, let's look at ions. So because protons are positive and electrons are negative, the charge on an ion is protons minus electrons, as shown here. The two types of ions, cations are positively charged, that has more protons than electrons, and that's formed when an atom loses electrons. Anions are negative, and it's formed when an atom gains electrons. We can't change the number of protons in an atom in normal chemistry. That's, again, because that would be sort of a nuclear reaction, like a fission or fusion reactor. So all we're doing in chemistry is gaining or losing electrons, not changing the nucleus in any way. Some examples of different cations and anions, again, representing that as those superscripts. Okay, now let's go to our last example problem here. You can try to complete this on your own, and then I'll give my solution afterwards. Okay, so here's the start of the solution. For this first one on the left, we're given 17 oxygen. So again, looking at our notation, oxygen is the chemical symbol. Based on that, we know that this atomic number is the protons. We left it off, but it is 8 protons there. Oxygen always has 8 protons, just that's what makes it oxygen versus a different type of atom. Now neutrons, that's based on the mass number. So remember that this number up here is the mass number. And the mass number is equal to the protons plus the neutrons. So the protons is 8. That makes, to make 17, we need to have 9 neutrons. There's no charge, so again, since there's no charge, in general, charge would be equal to protons minus electrons. But in this case, there's no charge, it's equal, so equal electrons to protons. Next, for nitrogen, the second one here, it's 7 protons. So again, 7 protons gives us the atomic number of 7 for nitrogen. The mass number that goes in that top left is going to be equal to 7 plus 7, protons plus neutrons. So that gives us 14. We could put the number of protons of 7 as a subscript there if we wanted. That's up to us. Maybe I'll do that here just for convenience. And then the charge, protons minus electrons, so that's going to be equal to 7 protons minus 10 electrons, which gives me a 3 minus or negative 3 charge. Yeah, more electrons makes the atom more negative. Just sometimes people get that flipped. Importantly, note for like 17 oxygen here, even though on average oxygen has a mass of 16, this particular isotope has a mass of 17. So you actually never really end up using the mass in these problems. That's just sort of the average mass, which is useful for stoichiometry, but not useful for this type of problem. Okay, the next part, we have 11 protons and 12 neutrons, so we can identify 11 protons that this is a sodium atom. Then the mass number is 11 plus 12, which is equal to 23. The atomic number again would be 11 if we want to put that in there. And the charge, in this case, our charge is 11 protons minus 10 electrons is equal to plus 1. So sodium plus. For the last one, we have 23 protons, so we know that it's a vanadium atom, but we don't know any other information. We don't know anything about the number of neutrons, we don't know anything about the number of electrons, we don't know anything about the charge because it didn't give us enough information to determine that. Okay, here's all of those answers together. That's the end of the new material for this. I also just have this overall summary slide with some of the key information. I try to build these up as we go along, and so that you have access to these as you get prepared for the quizzes and exams. Good luck.